Tēnā koutou e rangatira mā, tēnā koutou katoa, ko tainai nei, I runga I te nākau tautoko I tēnei pō. Nō reira, e te whakamanenga, nā mai haere mai koutou, tēnā rā tātou katoa. Ladies and gentlemen, my name is Neil Quigley. I'm the Vice-Chancellor of the University. It's my pleasure to welcome you here this evening to this Inaugural Professorial Lecture. This is a series of lectures in which we showcase the work of the new professors in the university, provide them with an opportunity to tell their colleagues and members of the wider community about the work that they're doing, and of course the work that provided the foundation for their promotion to professor. Tonight we're acknowledging Bernhard Pfahringer's promotion to professor in the Faculty of Computing and Mathematical Sciences. Bernhard, of course, is very well known to his colleagues, having been head of the Computer Science Department since 2013. Bernhard completed his undergraduate study in 1985 and his PhD in 1995, both at the Vienna University of Technology. His thesis was entitled Practical Uses of the Minimum Description Length Principle in Inductive Learning. The thesis tried to provide answers to the following conundrum. Simple models are easy to understand, but often not accurate enough. Complex models are much harder to understand, but tend to be much more accurate. Minimum description length offers well-founded ways to strike a balance between these two conflicting goals in empirical analysis. In 1996, Bernhard left Austria and came to the University of Waikato for a year as a postdoctoral research fellow in the machine learning group. He then returned to Austria to work at the Austrian Research Institute for Artificial Intelligence until joining the University of Waikato staff in 2000. He was promoted to associate professor in 2007. His area of expertise is machine learning and data mining, which is the computational process of discovering patterns in data involving methods at the intersection of artificial intelligence, statistics, and database systems. As a computer scientist, he is always building, evaluating, and improving tools for this task. The most recent tool is the development of the massive online analysis data stream mining open source software suite. MOA, Massive Online Analysis, is the most popular open source framework for data stream mining. It includes a collection of machine learning algorithms and tools for evaluation. MOA is a younger cousin to WECA, Waikato Environment for Knowledge Analysis, specializing in data stream mining. Traditional methods struggle in such scenarios or are simply not efficient enough. Bernhard has edited 3 books, published 20 journal articles in journals such as the Machine Learning Journal and the Journal of Machine Learning Research. He received a Marsden grant from 2003 to 2006. It was the associate principal investigator for 2 Foundation for Research, Science and Technology grants, won a Build IT grant for a postdoctoral research fellow to work with him and Professor Jeffrey Holmes on data stream mining, and has sourced multiple PhD scholarships for his PhD students. Bernhard is also a member of the local machine learning research group that won the 2005 SIG-KDD Data Mining and Knowledge Discovery Service Award for its WECA data mining platform. Ladies and gentlemen, please join me in welcoming to the lectern for his inaugural professorial lecture, Professor Bernhard Pfahringer.
Good evening. Thank you, Vice Chancellor. Thank you, Jeff. Hello, everybody. Colleagues, friends, students, Hamiltonians. The theme for this evening is the dawn of the age of data. So what I want to do is actually not just going to talk about my own work, but take a little step back and first of all, kind of give you a little bit of background about myself so they get a better understanding of where I'm coming from, and then want you to reflect on the amazing times we're living in, and just mention a few things that are really obvious once you see them, but you never think about them and take them for granted. So hopefully there's something in there that's interesting for everyone. It won't be very technical. So if you're a computer science student, maybe you get a little bit bored, but maybe it's a good review as well for you. Okay, so to start with myself. I don't speak Maori, but I really like the way you introduce yourself in a Maori context, and so I've decided to do that with the first few slides. So this is my mountain. This is an amazing number of mountains in winter to go skiing, like for instance, this is my laser pointer. There's a ski field here just on top of the city. And if you're lucky, if school finishes early, you can go skiing after school. So it's brilliant as a kid to live there. Now, this is my river. This is an interesting river because it's got a funny color. It's usually grayish or green, and this is because there's a lot of glaciers around, and you basically have all the sediment that comes from that. And as you can see, in summer there's less snow on the mountains, but the weather's kind of variable. It's a bit like Queenstown, probably, without the lake, but much bigger, more the size of Hamilton, maybe even a little bit bigger these days. Now, this is my tribe. When they dress them up in the traditional clothing, which is actually quite colorful, and probably most of you will be reminded of Oktoberfest, which is in Germany, but this is Austria. But it's very close to Germany, and so there's a lot of similarities between the south of Germany and Austria, including the traditional clothes. And if you kind of focus more on the more local aspect, so this is my hapu. This is the place I'm really from, Innsbruck. If we're having a good time, we can have that in summer or in winter, and there's a lot of stuff happening there, and like around the river, you can have big parties, or you have nice fireworks at times, and all stuff like that. So this is where I grew up. This is where I initially even went to university for 1 year, because when I finished high school, I wasn't really sure what I should study, and there was a couple of options, like some sciences were on the list, biology and chemistry, or maybe math and computer science. And I made this decision, well, in Innsbruck you could do math with a minor in computer science. Why not give that a go? And I liked it so much that I decided computer science shouldn't be a minor, it should be the major. But at that stage you couldn't do that in Innsbruck, so I had a big move. I moved to Vienna. And back then, in the early 1980s in Austria, this is like a big thing, because even the language is different there. There's a very different way of speaking German in Vienna than to Innsbruck. So it's maybe a move from Invercargill to Auckland, if you want to get a comparison. And there are multiple universities there. This one is a technical university, which is, I think, ranked in the 200s. So it's not in the 100s, but it's a good place. And they have this nice old building from the times of the emperor, but there's, of course, modern buildings around as well. And they have some really good programs, including computer science, and this is where I spent my undergrad studies, and then later on also did my PhD. Now, the real cool thing about that was the opportunity in 1984. Summer 1984, I got this offer to be a summer student at CERN. So CERN is this European Center for Nuclear and Physics Research that is on the border between Switzerland and France in Geneva, close to Geneva. And it's actually quite interesting in the way that, so this bit here is Switzerland, and over here is France, and CERN itself is actually extraterritorial, which is great because you don't pay taxes. So I could keep all my money. And the other good thing is that back then there were border controls. There was like really strict controls here. But if you were working at CERN, you could get in here and exit over here on the French side without any controls. So I was based here in this building that you probably would call a data center these days, because physicists collect enormous amounts of data. Really, it's mind-boggling numbers of. And even back then, so this 30 years ago, they had these huge installations here, so the whole basement there was basically for storage, and I'll explain in a minute. Interesting thing for me, that was also my first language issue. And it was not, this area is French-speaking, that was reasonably okay. It was my supervisor. He was Scottish. And the first 2 weeks, I had a really hard time, because he was really Scottish. Like, he was practicing bagpipe, playing with 3 of his Scots friends every Monday at 5 p.m. in this parking lot, marching up and down. And everyone knew about that, because you hear them for kilometers. Now, CERN is brilliant if you're a computer scientist, or maybe just a geek, because those physicists have money, and they need good computing infrastructure. So they always have the latest gear. So back then, in 1984, they had this, one of the things they had was this IBM Mass Storage System, MSS, 472 gigabytes, which doesn't sound much these days, but back then it was a big thing. So just to give you an idea, the basement was filled with racks that kind of looked like this here. So this is like a beehive, and you have, this is like a Coke can. So cans in there, and inside every can is about 20 meters of tape with a capacity of 50 megabytes. And for this amount of data, you need about 10,000 cartridges. So there was about 100 of those in the basement, and there's little robotic-like things that can actually retrieve those, put them into a reader, and you copy them into a hard drive, and then you can actually run your program. Now, just to give you an idea how big that was in comparison to what was the norm then, in the same year this computer was released. And I'm sure you have seen that before, and maybe you have had one or used one before. So I was owning one of those, slightly later model at some stage. This was 8 megahertz. This was 128 kilobytes of RAM, and it didn't have any hard drive or stuff like that. It just had a floppy disk of 400 kilobytes, so 400 versus 400 gigabytes. So there's orders of magnitude in between, and a very tiny screen, and black and white only. Now, this gets us to what I want to explain to you, what has happened, and which you may not have noticed. There's kind of a revolution going on, but it's kind of incremental and gradual enough that we don't really notice. So the first revolution is what I would call the hardware revolution. Now, this is an amazing computer that you see up there. It may not look like a computer to you, but it is. And it's only like marginally a phone as well, in my point of view. Now, if you look at its properties, it had 320,000 times as much storage capacity than this little old computer. Or in other words, 4 of those iPhones would replace the basement of CERN in 1984. So the whole basement, basically, you could store that in 4 of those iPhones. And of course, access would be much faster as well. You wouldn't have the robot picking the can, and it takes like a couple of minutes to read stuff. And in addition to that, you get much more working memory, you get a much better screen, it's actually a touch screen, and you get all this other stuff. You get cameras, not just 1, but 2. You get GPS, you get an accelerometer. You actually have the ability to pay, like with a credit card. You have apps for everything, so it's not just browsing the internet with Safari or Chrome or whatever. You have dedicated apps as well for anything you can wish for, and if it's not there yet, you just talk to us and we will implement it. So there was a hardware revolution. Then the other thing that happened over the last 30 years is what I'd call the network revolution. In 1984, there was no World Wide Web. There was kind of a predecessor of the internet, and was something like emails, and there were like very low-level capabilities for a select few people working at universities and in some research institutions. It wasn't something anyone would be using every day. Then in 1989, and that's just a coincidence that happened at CERN as well, it was kind of the birth of the World Wide Web. And you've probably all heard the name Tim Berners-Lee before. But 10 years later, the now prominent search engine started. It wasn't the first one, but it was just so much better than all the alternatives at that stage that basically it blew them away. And has captured the market ever since, and still has a large percentage of that market. And then in the 2000s, we saw something that we hadn't seen before, something completely new, social networks. And again, they're not the first ones. There was others before, like before Facebook in New Zealand, something was very popular with teenagers was Bebo, and some of you in the audience might have used it yourself if you're still a student. And then 2006 we got Twitter, 2009 we got WhatsApp. And that all had interesting consequences. But I think the main thing, and this is the thing that we don't really see that easily usually, is that we've turned and we're turning everything into digital. And this is, I think, the real revolution. This is what makes this century very different from the past. So my claim is that, well, in the history books in a few hundred years, you will read something about that this was the century where everything turned digital and where it was really a sea change. And the consequences of that is that if it's digital, you can easily store it, like on these drives, on your phone, wherever. And then once it's stored, it's also easy to analyze it. And this is where our specialty comes in, where data mining and machine learning now can thrive on all the data that's there. And I think an interesting observation there is that there was no master plan behind that. That has just happened. And it's mainly happened because of convenience and also because of interesting business ideas. So, if you're not convinced yet, I'm going to show you a number of examples to try to convince you. It's really amazing how everything is now digital. And when I prepared those slides, I was surprised myself at some stage. So first of all, photos. You take pictures. And we've always been taking pictures. But back then, 1980s or so, you had a camera, you had film, you took a few pictures, you went to the chemist, you had them processed, and then you stick them into a album like that, or if you had slides, maybe you do a projection, but usually you had one copy of a picture. And actually, these copies were pretty good because they last pretty long, and unless you move house and lose your album, usually they would be lasting for decades. Now, all of that has been replaced basically by digital cameras, if you still have a dedicated camera, or by phones that have cameras. And the prices are also amazing if you think about it. Like dedicated digital cameras, small ones, you can get for a few $100s, and they are even waterproof, so you can snorkel and film while you do that. Something that's was unthinkable 30 years ago. You would have to spend a lot of money on really professional gear to be able to do that. And the quality that we get these days is even better. And so you get sites like Flickr or Facebook where you have all your pictures. If you have your mobile phone set up the right way, it might even be the case that you take the pictures and automatically upload it. So one word of caution here, everything digital may not last that long. So if you only have a copy on a hard drive, and that hard drive might last 5 years or 10 years, and then it's dead, you've lost the copy. So always make backups of everything that's important to you, like your family pictures or your phone, because your phone is a computer and it needs backup like your computer does, if you value the content on your phone, and I suppose you should. So that was photos. Navigation, other example. We all used maps, printed maps, trying to find our way around foreign cities. The map might have been out of date by 5 years and we get stuck, and it's not good fun. These days, it's very easy. Like you have this GPS, like this taxi here in Tokyo, or you just use Google Maps on your phone. And it's brilliant because, first of all, it's usually correct because it's usually updated in real time. And it might even be better than the map because it might know about conditions like there's roadworks ahead, so it might route you around. And also, it's much easier to follow the orders by a machine than the backseat driver, right? So this is an amazing step forward. Money. We used to use coins and notes all the time. I bet in this audience, at least 20% of you wouldn't have a single coin or note on you today. Maybe even more, because New Zealand is actually one of the very advanced countries in that regard, where a lot of things around money have moved to being online already. So what we have these days is this, of course. And you have F-Post or credit cards, basically. It's also advantages like if you lose your card, well, you talk to your bank to cancel it and you get a new one. You don't necessarily lose any money. If you lose $1,000, they're probably gone for good. So that's really good. Also, because of this, things change. Like, I remember once in my life, I was actually carrying probably the equivalent of 15,000 New Zealand dollars on me by basically going to a bank to make a deposit for an apartment. These days, that would be crazy. You wouldn't do that. It's probably, if you have that amount of cash on you, it's probably dodgy for some reason. Communication. Ah, good old letterbox there. When was the last time you wrote a letter? And I don't mean filling out a form that we were asked to fill out for some government department or whatever. Really a letter to a friend. For the younger ones, they may have never done that actually. Or phones, like good old phone boxes. There's still phone boxes around, but Telecom is repurposing them as Wi-Fi hotspots. So these days, well, actually, that's interesting because it's also already more like a dying technology. Text messages were very interesting because they were kind of an afterthought, but they were really successful. And up until maybe 5 years ago, they were a really easy and cheap form of communication, like our emails, like Gmail or other providers. But emails, again, have replaced letters, but they're not very fashionable anymore. So they're used by old people and by people running businesses. So I use email a lot. Like the way I work is run through email, and even my to-do list is basically my inbox. And but for my students, I really have a hard time making sure that they actually read their emails because they're not really used to that anymore. There's faster channels of communication. So Twitter is kind of more public, but more private messaging, like WhatsApp is a very popular application that has probably replaced text messages. The nice feature about WhatsApp is that it's international. So with your text message, in New Zealand it may be free, but if you want to text someone in Austria from here, then maybe $1 or so for a simple text message. With WhatsApp, well, there's no cost, so that's brilliant. Okay. Next area. Well, we already had social networks, so I just want to mention Facebook because they're really dominant, and Twitter, and another one, LinkedIn, because that's really a useful network for professional purposes. And these are kind of the global ones, generic ones. There's a lot of specialized networks for lots of different things. So for instance, if you're a researcher, you might have a profile on ResearchGate, and there's another one called academia.edu, and there's specialized networks for a lot of purposes these days. Now, information and knowledge, the way it's shared, well, it used to be printed, like newspapers, books, you go to the library. That has stopped, basically. Even I myself, who sometimes tends to be a bit old-fashioned, even though I'm in this area, and I've been going to the library regularly, probably longer than many, but I probably haven't been to our library in at least 2 years or 3, because everything's online now. So newspapers, but also scientific journals. E-books are a very useful thing, because if you want to go someplace and don't want to carry like 50 kgs of books, you have one 500-gram e-book reader and you have thousands of books on it. Wikipedia has basically put the Encyclopedia Britannica out of business. Printing encyclopedias doesn't make sense anymore. It's all online. The problem with online is finding things. It can be very easy because we have excellent search engines now, like Google, Bing, Baidu. But you have to be very focused. You need to know what you're looking for. Like browsing, serendipitous discovery is not really supported that well. And this is maybe where librarians still have a function these days. But also there's something which is called recommender systems, which tries to kind of help you in that area. But it's not perfect yet. It's pretty good, but it could be better. Okay, I haven't finished yet. There's still more, and there's many more, I think. A few more here. Audio and video, of course. YouTube, big one. Netflix, more of a business. And Netflix has really captured the market. So there are estimates that in the US, on any weekday evening, 30 to 40% of all the internet traffic is generated by streaming video through Netflix. So So it's basically this company almost monopolizing the use of the internet in the US every evening. If you think about it, it's just crazy. Spotify. So radio. Radio is interesting because the radio stations actually still survive. And this is probably because radio is an interesting medium. Video, you need to focus on it, you need to watch it. Radio is kind of like, you can do reasonable stuff, you can work on something, and still have radio in the background. So radio is still popular, but all the radio stations now have online channels as well, and you see more and more services that just stream music, like Spotify and others. I mentioned Spotify is probably the most well-known one. Another thing that hopefully you have heard of, and if not, really go there and check it out. TED is amazing, TED.com. It's a collection of talks on technology, entertainment, and design from across the world. And there are TED events that usually run for a day. And we also have them here in New Zealand now. There's a regular one in Auckland. We had one in Hamilton in June. And I think that's going to be repeated. If you have a chance to, at least, if you're bored, if you don't know what to do, go to TED.com and watch a random movie there. It's going to be good. This is an interesting one, personally for me, because this slide I added just yesterday, almost as an afterthought, because I had completely forgotten about it. Probably just shows you that I don't spend much time shopping. But of course, this is really big, like Amazon. Everyone has used it before, and there's a local equivalent which is actually doing pretty well. Or for secondhand stuff, there's eBay internationally, and we have TradeMe here. And they're really good. And it's convenient, and it's excellent to have. And it has completely replaced what we had like on paper before. Oops, that was the wrong. Nope. What's up here? Oops, this is interesting. Maybe just restart it. Yep, always works. So, okay. So my claim is that, as I said, there's something that has fundamentally changed. And it's a really huge change, even though you may not notice that. And so I think it's really similar to when we, as humanity, we came out of the medieval ages into the area of enlightenment, the Renaissance area. And so to cite some really famous physicists from that area, Galileo Galilei, what did they do as scientists? Well, you want to measure what you can measure, and all the other stuff you want to make measurable to further science. Now the same thing is happening with digitalization. So we have a lot of digital things already, as you should be convinced by now. We can store and analyze that. But we also need to, and we do that actively, digitize what's not digital yet. Okay, that's going pretty good. So, and now finally it actually comes to where do I come in? What's my sub-area? What's my specific subfield in computer science? Well, I'm going to use the terms data mining and machine learning interchangeably here. There's enough of you in the audience who know that this is not 100% correct. Please bear with me. But I think the distinctions are kind of blurred anyway already. So basically what we do is we look at the stored data and we try to find some interesting information in there. And usually that means some patterns that are recurring in some way. And they don't necessarily have to be frequent if they are interesting. And this is good for two purposes. So we want to understand the data, or better understand the data, but also we want to be able to predict. Well, at times at least, we want to be able to predict. And if you look at this field, it has grown organically with input from a number of different fields, and mainly mathematics, statistics, and computer science. So it's kind of perfect to be in a faculty that covers exactly the three subjects. And in terms of mathematics, optimization is mainly important. In terms of computer science, there's two very distinct subfields, artificial intelligence and databases. Personally, I come from the artificial intelligence side, and that also explains some of my prejudices, probably, and approaches. And I've just tried to give you an idea here what it is to be a computer scientist. It's an oversimplification, but I think it captures it to some degree. So basically what we do is we invent and build and analyze and improve algorithms and programs. So an algorithm is like the recipe, like a pavlova recipe. So we write pavlova recipes. Then you have a lot of cooks who cook their pavlovas according to the recipe, but the outcomes are all different. They're all pavlovas to some degree, but with slight differences. So the same algorithm can be implemented by different programs and have different specific properties, and it makes it interesting. There's a lot of diversity there. So in a way, being a computer scientist is like being a toolsmith with the ultimate tool maker, because you can turn your computer into anything you want. If you can imagine it, you can make it happen. And with that, I want to give you some light-hearted entertainment for 2 minutes. I'm sure some of you recognize this already, but if not, then you probably haven't seen this movie from 1968. So it's actually a long time ago, almost 50 years. So this is, you forage around, you look for ideas. You have some colleagues around. You don't actually communicate that much. Then you find something interesting, something like a serendipitous discovery. You have a closer look. Then there's a light bulb moment. That's brilliant. If you get one every year, you're really, really happy about that. You have a very close look. And then suddenly it dawns on you that what you've seen for a long time, actually, you can make connections to other things that you've seen before and combine them in new ways or use them in new ways. So you pick up that tool any minute now. You investigate it a little bit further, and you find a new use for it. Okay, so you have a new tool. Of course, the problem with the tool is once you have one tool, like a hammer, everything looks like a nail, right? And so this is a little bit the danger that we have to live with. Now, talking about tools, I want to introduce you to the first tool of this evening, which is Weka, which has been mentioned before, which is really well known around the world, which is actually Ian Witten's brainchild, but also Iber Frank and Mark Hall have done a lot of work around that. So Ian's still a professor with us. He was only partly retired. I was an associate professor. Mark Hall used to be a lecturer, but is working for a company that provides commercial support for Weka. And it's an interesting tidbit that that company has been bought by a larger company this year, and I'm sure there's going to be some announcement at some stage later this year that the university made a little bit of money out of that as well. So even though we make our software freely available as free open source software, you can still get some money out of it. It's, as I said, being used a lot, especially for education, but also for applications. There's also this so-called MOOC. So you're going to learn a few abbreviations this evening, like FOSS, free open source software, MOOCs, massive online courses. So you can learn at your own pace if you want to, and if you don't have the time to enroll in a university course, they've written this nice book. Weka was basically the reason I came here, because there's a machine learning group that's built around this tool, and that was really the attraction for me to come to New Zealand from a professional point of view. It was started in the mid-90s. I came here in 2000, so I'm not one of the main people, but I've contributed my fair share over the years. It's actually a small number of classes where I'm one of the authors of the codes. I've done some programming for it. But I think more importantly, I've supervised students who have contributed. Some of my grant money has helped to finance support for it, and so on and so forth. So using this tool, what I want to do now is, I'm not just a researcher, I'm also a lecturer. So I want to teach you one thing today. I want to tell you about two data mining methods, and I want to explain one in more detail, because that's a very simple and useful one. It's called decision trees. And to do that, we're going to look at a very simple data set that's brilliant in a way. It's the passengers of the Titanic and trying to find out who has survived, who hasn't, and can we find some explanations for that. Now, if you Google for data on that, you will see there's an awful amount of information on the internet, mainly because of the successful movies. So some nice folk have made this data available where we look at about 1,300 patients and we have a lot of information about them. It's all anonymized, there's no names anymore, but we know the passenger class, so the 3 classes, 1, 2, and 3, whether the male or female, the age, and this is, well, child of 11 months probably, that's a funny point, 0.91. The number of siblings, that may surprise you, but there were quite a lot of families on board. The number of parents, so lots of people didn't have their parents, like a regular passenger, but if you're a child, you may have 1 or 2 parents traveling with you. The cabin number when it was known, and whether you survived or not. Now, if you analyze data, it's always good to look at it. And when I say look, I mean visualizing the data. So Waikato has a number of different ways to do that. The very simple one is this one, where you just basically look at, for all the features that you have, how do they correlate, the values of those features correlate to the outcome. So the outcome is our survival. So we have 500 survivors, and we have about 800 people who drowned. So this looks bad. Some of the passengers, for the crew it was even worse. I think the survival percentage for the crew was less than 15%. But for the passengers, what you see is, well, there's maybe not much difference between first and second class, but definitely in third class, many more of the third class passengers drowned. Also, if you look at, this is female, this is male, well, many of the females survived, but many of the males drowned. With age is not so clear, even though here, like this is probably around maybe 8 years or 10 years, it's actually quite a lot of children that also drowned. Usually you would think women and children first, and it may be true for the women, but maybe not for the children in this case. And then right now, there's probably not much we can say about siblings and parents. Here, there's a real big number where we don't have a number for the cabin, so this is a value of 0. And then there's a lot of different. And this is an interesting fact that I didn't know about the Titanic before, that actually had 3 harbors. That started in Southampton in England, moved over to France, to Cherbourg, and then back to Ireland, to Queenstown. And so depending on where you board it, you can see that this may be similar percentages, but here, this is Queenstown in Ireland. A lot of those, percentage-wise, actually drowned. And we can ask why, and there may be an explanation for that in a minute. So decision tree is, some of you may have seen decision trees like in biology before, but like old books where you look at some feature like it's got 6 legs, it's an insect, it's got 8 legs, it's a spider, and you can kind of go further into more detail. Now here, what we have are programs that look through the data and basically try to set up such a tree by looking at what's the most useful feature. And let's use that to split our data into 2 subsets first. So in this case, the program's picked up on being female or male. And if this, unfortunately, maybe not very intuitive, but basically what it says is, generally, if you're female, you had a good chance of survival. And there were 466 females on board, and all of them survived except for 127. So these are the exceptions. Over here, for the males, it's a much worse picture. On average, you did not survive, you drowned, and there were 843 males, but out of those, 161 still survived. So these are the exceptions to the general rule. The rule says you would drown, but if you had some luck, you actually survived. Now, we can take that further by adding more levels, more finer distinctions, to maybe get more interesting patterns. So our algorithm, it's not us doing that, it's really just the machine deciding that all by itself, decides that for the female branch, we're going to look at the passenger class. And if they're first or second class passengers, they had a very good chance of survival. There's 250 of them, and all but 17 survived. If you were third class, unfortunately, the picture doesn't look so good for you. There was 216 and 110 drowned, and 106 survived. So it's about 50-50 chance if you're third class. On the male side, the system has decided we look at cabin numbers. If you don't have a cabin number, then you probably did not survive. If you have one, you also did not survive. So that looks odd. But the reason for that is actually the percentages are very different. If you don't have a cabin number, then you had a high chance of drowning. If you had one, then your chance of survival is up to 40%, 60 out of 150. And we can go on and on and on, add one more level. Tree is too big, so I'm looking at the left-hand side only. Add one more level. Now something interesting happens, because I asked the system to add one more level, but it refused here and here. Because from the system point of view, we don't have enough data to actually look at a more fine-grained distinction. And those nodes look pretty good enough already. So there's 144 and there's only 5 exceptions. Or here there's 3 exceptions out of 21, so the system stops. Now, looking at all that and trying to make sense out of it is something the machine can't do. The machine gives you the patterns, and then you might start looking at it and thinking, can I find some explanations? And the main explanation is the third class thing. Third class is at the bottom of the ship. And so it's the hardest place to get out to the lifeboats. And you can see that very clearly, that if you're in third class, your chance of survival are pretty slim. Especially if you're male, but even for women and children. And then also if you look at like the distribution of third class, were mainly people immigrating from Europe to the US. Whereas first and second class passengers were either really tourists, especially in first class, or more like middle class professionals that had to go to the US for whatever reason. So this gives us, there's an interesting thing that you need to observe here. Even though it says strict yes or no, it's not really a strict yes or no answer. It's always qualified by these numbers, which you can turn into percentages. So in a way, our system is like a politician. You won't get a straight yes or no answer. It's always qualified with something. Yeah, it's a 70% or 50 or whatever. So you might want to ask, how good is our tree actually? And we have methods to evaluate that. And in this case, you get an estimate of about 80%. So it gets 80% of the predictions right. And for this data set, I've tried with a lot of different algorithms, because there's many different algorithms, and they're all about this number. They may be 81, 82, but there's no way you can improve, because you just don't have enough information. You would need more fine-grained information. Because another interesting pattern that someone found is not just the class, which relates to the level in the ship, but also the section. So in the middle section, apparently, is where most people perished. And you can deduce that from the cabin numbers, but unfortunately, there are not many cabin numbers known. So it's a bit unclear whether this is actually really a true fact. So just a summary, trees look like that. They're brilliant because you can look at them, you can understand them. They can work with numbers and with nominal values. They can kind of combine different things, like if you're female and your boarding class was first or second, then you survive. So it's really cool to have. They're fast to generate because for one level, you go through all the data once. So here we have 4 levels, we go through the data 4 times and we're done. It's brilliant. There's another very useful and successful class of algorithms called neural networks. They're kind of the opposite. They're really slow. So to train them, you have to go through the data hundreds, maybe even thousands of times. But also, it's worth it because they give you good results. They kind of like black boxes that are inspired by the brain, but don't really work like the brain. So you would have your inputs here, like the passenger class, and, your age, and the number of siblings. And then you have a weighted sum of those and some weird function happening here. We call that a hidden layer, a neuron-like thing. And then you have outputs of those, and you can recombine them again with different weights and have another interesting mathematical function happening. Then you have some outputs, like you predict whether the probability of survival, or you can have multiple outputs, like if this is data about patients that come into an ICU, you might have as inputs down there the heart rate and temperature and all kind of other things, and you might predict the survival probability, but also how long they will stay in hospital, how many liters of infusions they will need, all kind of things. These were very, very popular in the 1980s, and a lot of my friends that were studying at the same time actually focused on that and made a career out of it. But then it became a bit more quiet around them for various reasons, mainly computational reasons. They, as I said, they were way too slow. And also data was a bit of an issue. Now, they've seen a really strong renaissance in the last 3 or 4 years for a couple of reasons, but mainly because there were a few interesting new algorithmic ideas, and just our hardware has become so much better. So the algorithms give you a factor of 10. The hardware gives you a factor of 10,000 or maybe 100,000. If you combine that, you get 1 million. And now you can do things that you were just not feasible before. You can work with really large networks. So have not just 2 layers, you have 20 layers. And you have them really wide, like hundreds or thousands of units. And you feed millions of examples through it. And what that means is that you learn all those weights. So there's going to be millions of weights. And from a statistical point of view, that sounds nuts. Impossible, you would overfit. But no, with the new algorithms, it works. And it works really well. And so in a way, there's this new buzzword, deep learning. And it's deep because its networks are deep, because they have so many layers. And that has really caught on in the last few years. Okay. Oops. Now, my claim is trees and neural networks are the best algorithms that we have currently. How do we know? Well, we do know because the web pages like these web pages here that organize competitions that you can take part in and you can actually win some money, like it says $100,000 up there. So it's serious money. And you have thousands of teams competing and all kind of different things. Usually it's companies that want to solve a problem, but also maybe like data from CERN again here about physics. And if you look at that, who wins? Well, the winners for the money, they have to not just hand over the algorithm, but also write a description that's published. You look at it, image tasks, anything with pictures, neural networks win. Anything else? Huge ensembles, not just single trees, they're okay. If you combine them in interesting ways, you get the winners, and that's just what happens. All the other algorithms are interesting from a scientific point of view, in terms of applications. These are the 2 that you need to focus on. Now, just very quickly, I like this example. I use it every year in my AI paper. I Google for myself for images, because it shows you how bad that is. Google for text is brilliant. Google for images is bad, because yeah, there's some images up there of myself. If you look at Bing, I just want to badmouth Google. Some of the pictures you may be able to explain, like they're maybe co-authors or people who work at Waikato University, but half of the people, I have no idea who they are. Why are they up there? So it would be brilliant if we had a function like click on it that Google explains to you why it thinks this is a picture of me. Unfortunately, it doesn't. They know that this is all bad, and so they've hired these machine learning people, these neural network experts, to work on it. And there's a little kind of Waikato angle here. There's this guy that some of you may even know. Shane Legg, he got his BSc in Math and Computer Science here from Waikato in the early 1990s, then went on to Auckland and Switzerland, master PhD and so on and so forth. Started a company with 2 other very smart people in the UK, and last year Google bought that company for an amazing amount of money. And they basically work on deep networks. So what does Shane think about all that? Well, just listen carefully.
Graph. That's just completely nuts. Now,
yeah, he must have gotten probably a nice chunk of the billion. Okay, now, next tool, that's really, quote, my tool, but not just, everything's teamwork, and I'll show the team in a minute. So, there was also mentioned before, Moa. We like to use names of native birds. And it took us a long time to actually come up with something that we can claim is what Moa is abbreviated for. So it's massive analysis or analytics. We kind of changed that now because of marketing reasons. It's a very targeted system for a very specific problem. With all the data that we collect, if we collect it over time, it has interesting properties. And one of the most important one is it changes. And to be able to deal with change, you have to do specific things. And in Moa, that's all built in. In Vector, it's not as easy. You can do it in Vector, but Moa is more targeted and it's better fit for that. Again, like Vector, it's free open source. You can download it. We have Java. We don't have a MOOC yet. Maybe it will happen. We don't have a book yet, but we're writing one. And it can still fully interoperate with Vector. So if you're used to Vector, picking up Moa is pretty easy. Just people there. So, where's my pointer gone? This gentleman here, Richard Kirkby, started it all with his PhD. He was co-supervised by me and by Jeff. And he finished it. We make it open source. And this guy picks it up. At that stage, he was in Barcelona as a PhD student, frustrated with his software that was available to him, found Moa brilliant. I use Moa for my PhD. And he visited us. He was brilliant. We hired him. He was here as a postdoc for 3 or 4 years. Unfortunately, we then ran out of money, and he moved into industry for a few years, but now he's a professor in Paris, so he's doing very well. The other people here, just again, the advantages of open source. These three guys are from Germany. They, in a similar way, discovered more, started contributing, did a lot of interesting work on clustering. So he's now a professor in Munich at the LMU University there. This is one of the top-ranked universities in Germany, and also with like 70 or 80 in the world. So it's really cool to have him there. I'm going to skip this because in the interest of time, I'm just going to show you with those tools what can we actually do. I've just selected a few applications that I've been involved in over the number of years to give you an idea of the breadth, because basically, whenever you have data, you can apply our tools. You may not find something interesting, but at least you can try. So the first thing is rain radar images. MedService has this web page where you get rain radar. So again, this is the digitalization of everything. 10 years ago, they might have had the rain radar, but they will have the pictures and no one else had them. Now they put them on a web page. You can go there. You can look at it, but you're going to scrape it. Now, this is a picture for every 7.5 minutes. You want to know, is it going to rain or not after this talk, in an hour's time or so? Well, Luke's working on that. And currently, he's getting really good results. So this looks almost perfect. It's a little bit cheating, because this is only for 7.5 minutes, and it's interesting. If you predict an hour into the future, it's not as good, but it's good enough, and it still works. And it's actually, this is using trees again, so it's not an interesting point. Something different, Waikato, you have to talk about cows. No way around. There was already a few years ago, probably 5, I think, when Adam did his master's and looked at an interesting problem that the LIC posed to him. From data that you collect during milking, can you predict whether the cow's in heat or not, so whether it's time for artificial insemination or not? Well, this is kind of, this shows you how good the system is, and if it would be perfect, you would be up here. There's a lot of room for improvement here. Now, this is kind of the best he got, so he got some improvement, but it wasn't perfect. He was using trees again in some interesting ways. It was a success scientifically. He published, he got his master's. Application-wise, maybe it was a bit of a failure because it's not being used daily by LIC, but it got them interested, and they've hired 3 or 4 of our PhD graduates now. So maybe even from an application point of view, it was an indirect success. Again, totally different. Electricity is all being digitalized. You have smart meters at home. We know everything about your electricity consumption. This was a pilot, again, 3 or 4 years ago. Just a couple of 5,000 households in some suburb in some large city in New Zealand with some company I can't name. Peter Reutemann, the research programmer, was heavily involved with that. This is the profile you would expect. High peak in the morning, another peak, but a wider peak in the evening. And this is actually true for a number of those 5,000, like a few hundreds, but not for all of them. Now, this is a different one. It kind of looks similar in shape, but has different properties. Like there's always a lot of electricity being consumed all the time, and there's a lot more at night. So maybe that's winter, and people are heating a lot. That's a fair assumption. If you get that picture in summer, something's wrong. Maybe your hot water cylinder is broken and just burns through electricity. And you get this. Any guess what that could be? It's pretty flat, but it's not 0. And the scale is actually different. It's a larger scale, so it's only like 0.2 and 2.5. This is the average on Waitangi Day. People don't consume much electricity. And also they have no peaks. They get up early, some of us, and some get up late and use more electricity during the day, but it's very different. Now, this is very interesting in terms of average of consumption, so for supply side management, networks, but also personally, if you can compare your household to the average household in your neighborhood, you know how you do in comparison. And maybe you're doing really well, or maybe there's something that you might want to look into. Yet another application, again, totally different, but again, internet, tweets, digital data. Tweets are really useful because you can interpret them and can try to find interesting things. Like some of them have smileys, and so what we try here is from the smileys and from a small lexicon, where we know that happy is a positive word and sad is negative and so on. We try to kind of learn for new words to predict something like you find on Twitter, LOL, it's probably positive. Someone says grr. It's not really a word anyway. It's a strong indication of some negative feelings. Vector is neutral, unless it's the company, maybe. But then it would probably be capitalized, and even if not, then here we would have some information that this was actually the name of the company. So you can do all these different things with our tools. It's really up to you to kind of come up with what you want to analyze and how you want to do it. Okay, just a new buzzword. You've heard about big data. Now the next thing is little big data. It's your personal data. Because if you think about it, with all the stuff being digital, you generate a lot of digital information every day. And if you had a way of putting that all together and analyzing that for yourself, or have someone analyze it for you, it could give you very interesting insights about your behavior. Maybe if you have like health data, it could also help there. There's a lot of potential there, I think. But that's something for the future. And I'm kind of close to wrapping up here. That's good. So I make a few suggestions what I think you should ask companies for and what you should ask your member of parliament for, the government. You want better technology. Our internet is still too slow and too expensive. Fiber is okay, it's getting there, but especially mobile is not competitive in international terms. I was lucky to spend 3 weeks in Austria last year. I can get unlimited mobile internet for $30 a month. And I was using 30 gigs in 3 weeks. Because once you have it, you use it for everything. I was actually, it was a bit of an experiment, wasn't using my mobile phone, I was using an iPad, so that I can't make phone calls unless I use Skype or something like that. It works perfectly fine, and especially it's brilliant because there's no roaming. If I Skype someone in New Zealand or someone in Germany or someone in Spain, it's all the same. So kind of a legal point of view, I think what we actually want is we want to be the owners of our own data. Right now, you use Google, you use Facebook, whatever, you click terms of conditions accepted without reading, because everyone does that. They own your data. I think what should happen is that actually we own the data and we only grant them a license to use our data. And then you could have something like an official information act, not just for governments, but for companies, so that you have the right to ask the company, what data do you store about me? Because it could be useful, like they may have things gotten completely wrong and you might want to be able to correct that, or you might want to do your own analysis of your own data. And we want to have free access to publicly collected data, which is actually in New Zealand really brilliant already. It's a lot of stuff that Statistics New Zealand and various government departments make available. For instance, you can just download a file with 500,000 records of road accidents from the last 15 years. You analyze that, you find the number one reason for accidents is not speeding, it's not being intoxicated, it's tailgating. So don't tailgate. And the accident rate will come down by at least 25%. And you want to have decision making based on data, on information. What do we need to do? Well, I mean computer science and especially data scientists and specifically, need to get better at educating people about probabilities and what they mean and averages, medians and stuff. Our tools need to improve. They need to be able to deal with larger data in faster ways. They need to become simpler, more user-friendly. Currently, what we build is for experts, but you would want to have something like Excel that everyone can use to analyze their own data. We're going to also take more advantage of what's being produced digitally. Right now, it's really mainly for advertising, if you look at Google and Facebook, whatever, and also surveillance, of course. But I think there's a lot more opportunities, like in health or with transportation. So for instance, with your GPS and with your mobile phones. If you think about, like, Hamilton's not bad, but Auckland, Southern Motorway. You're on the Southern Motorway Monday morning, you want to go to the CBD, the motorway is full, even without accidents. The mobile phone providers know about that because they know all the phones are there. So you could be smart in rerouting people. Like if I actually don't want to go to CBD, but I want to go to the airport, and there's some blockage between Takanini and Manukau, I could be routed off the motorway already in Takanini. So probably much better, even though it's morning rush hour. If you route everyone off the motorway, then you just move the problem to Great South Road. So what you want is kind of a system that has an overview and partially reroutes some users, so that kind of a load balancing going on, so that you make best use of all the channels that you have. And there's people working on apps for that, so it's not just an idea. Better X can be anything, like education here, helping struggling students, picking up that they're struggling through Moodle, stuff like that. It's being looked at. Okay, time to finish. So this is a list of all my co-authors over the years. I hope I haven't forgotten anyone. Some of you are here. It's about 70, and I'm adding new ones as we speak. And maybe before I go next, she also mentioned that if you look at it, the names, you can guess for some of those. So they're kind of quite a number of different places. Of course, there's still a strong focus on Europe. So it goes from Portugal and Spain and France and Italy and Germany and Austria and Slovenia and Belgium and Netherlands and Lithuania, of all places. Also New Zealand, of course, and China and India and South America, Chile, Brazil. It's getting there. Be really international. I want to say a big thank you to everyone in the group. This is more or less a complete list of the current members. There's always space for new ones, as you can see. Your picture could be here. I have to say a big thank you to especially Ian, because he's the reason I'm here. He convinced me twice to come here, first for my postdoc and then later for a permanent position. I think it was a good decision, both for my career but also for my family. So I'm really happy. Thank you, Ian. Also Jeff, in doing an amazing job over the years, and everyone else. And this brings me to my last slide and one prediction. And I should have made that a capital F, I think, in hindsight. So you all remember this, right? It was 4 years ago. It was really close. It was a nail-biting final. So my very unscientific prediction is this. We're going to have a repeat. It's going to be equally bad, but it's a 51%, so that's it's positive, but it's very close. And I'm hopeful that on Sunday we can increase that number at lunchtime. Thank you.
Okay, it's my job just to finalize proceedings now. So this concludes the formal part of the evening. I don't know how formal that was, but it was fairly formal, I think. I'd like to acknowledge Professor Pfahringer for his talk, which covered a great history, really, of the modern times and the kind of problems that the field of machine learning is dealing with on a daily basis, and hopefully be the field that helps improve our lives in the future. That's one of the big hopes anyway for the field. It should be mentioned that Professor Pfahringer was actually recruited from a jazz club in Bari by Professor Witten in 1996. I know this because they didn't invite me. Probably quite wisely, really. So I believe that was the origin of why he came here, probably after a few steins. But anyway, at least he came back again, because he's made an amazing contribution to the department and the field of machine learning. One of the things that's not well known is that at some point in history, in the last 20 years, where machine learning has become an extremely big field. Waikato had more people on the editorial board of the Machine Learning Journal than any other university in the world. So that shows you the sort of impact that the groups had in the field. And Professor Pfahringer was certainly one of those people that was on the list. So I'd like to know, actually, how many articles Bernhard has refereed. Perhaps he could estimate that sometime. But it's an amazing thing that he's done for the field, not just his own work, but the amount of refereeing he does and the contributions he makes, not just for the journal, but for all the conferences that he's on the program committee for. So I don't think I'm going to summarize the talk too much. I think it's an ongoing thing. Revolutions are always talked about in terms of history, looking back, and I'm sure that will happen, as Bernhard said, in 50 years' time. They'll look back and declare the 21st century as the age of digitization and machine learning, of course. So I'd like to thank you for attending the talk. It's wonderful for me to see so many people here. That's marvelous. And thank you for supporting both Bernhard, the faculty, and the university. The bar will be open once you leave the auditorium, where you can purchase your own drinks. So that's a very generous offer. And of course, if during this presentation you've come up with a few ideas of your own and you want to discuss them further with Bernhard, I'm sure he'll be happy to talk to you about them. So thank you very much.